Hello, friends. Today I will discuss about the integral and differential calculus. You know that integral differential calculus are used in various branches of physics, science, and technology. You can model and analyze the different physical quantities like velocity, acceleration, momentum, electric and magnetic field, and it is used in optics. So, for example, differentiating velocity with respect to the time gives you the acceleration. In similar manner, if you integrate the force with respect to time, it will give you the momentum. But few people know about the physical meaning of integral differential calculus. So, in my video, I will take you to the journey how to use the integral and differential calculus to solve the different numerical problems in physics, and also I will differentiation is a fundamental concept of calculus where we find out the variation of a function with respect to the input variable. Suppose say y is a function of x is can be written as y equal to fx, and here x will change after some time x plus of delta x, where delta x is very infinitesimal change in x and it tends to 0. Then to find out the differentiation, uh, to find out the rate of change of x with respect to x, we must find out the derivative of y with respect to x, and it is defined as dy by dx, or it can be written as f prime of x, and it will be by definition limit delta x tends to 0 and f of x plus of delta x minus of fx divided by delta x. So using this definition, we can find out the different derivative of different function. Suppose say if you want to find out the derivative of y equal to x to the power n with respect to x, then ddx of x to the power n will be n into x to the power n minus of. So this result will comes out from this formula. Again, if you want to find out the derivative of some cosine or sine function, suppose say dd theta of sine of theta, it is gives you the cos theta. Similar manner, dd theta of minus of cos theta is cos of theta equal to minus of sine theta. Similar manner, dd x of e to the power x is equal to e to the power x. dd x of log of x is 1 by x. So you first of all you remember those differentiation and you can use it directly in some numerical problems. Again, I will discuss about the physical meaning of the uh, integral calculus, differential calculus. Suppose say now y equal to fx, and this is a function, and if you plot this function in a xy scale, suppose say this is x is y, suppose say this is a polynomial type, so this is simply like this. And now if you find the derivative at certain point, suppose say this is the point, and this point is x1 comma y1, then a derivative of y with respect to x at certain point, suppose say x1 and y1, gives you the slope of the tangent at that point. So if you draw a tangent here at this point, then if it is theta, the angle make with the positive direction of the x-axis, then m, which is the gradient of the slope, is equal to tan theta, is equal to dy by dx. So this is the physical meaning of derivative with respect to x. So if you just observe closely, there are several point of maximum minima of this graph. Okay, and if you find out the maximum minima derivative at the point of maximum minima, we will get 0, because here the tangent will be parallel to the x axis, and in this case theta is 0. So m of tan 0 is 0. So dy by dx equal to 0 here. So just finding out the derivative and of a function and equate it to 0, you can get the point of maximum minima of a certain function also. Now I start discussing the numerical example. The first numerical example is in the arrangement shown in the figure 44. The ends PQ of an unstretchable string move are downward with an uniform speed of u. Pulley A and B are fixed. Mass M moves upward with a speed of. These are the four options given here. Okay. So we need to calculate it. The upward motion, upward speed of M with the help of differential equation. So suppose take this is the x direction, okay, and this is the y direction, and suppose say as you see that this point is fixed. So this distance from the origin here is say a, and this length is L. If this two length is L, total length of the string is 2L, and if if we take the y displacement is y, then using Pythagoras we can write down the L square equal to a square plus of y square. Okay. Now, first of all, you need to know some initial condition here, because you know that the PQ points are moving downward with a speed of u. So you must know that the L by dt, that is the rate at which the length L will change, is u. This is the condition, and you need to find out the dy by dt. This is the our aim. You want to find out the dy by dt. Okay. Now taking derivative with respect to t time of the equation 1, say, and here we use the formula that we have discussed earlier, that is ddx of x to the power n is n into x to the power n minus of 1. So here in this case L square, so 2 of L, and it is again dl by dt. Okay, and is equal to a is constant, so there is no change of constant thing with respect to time, so this will be 0, plus 2 of y dy by dt. Okay, so simply 2 will cancel out, so we need to find out dy by dt. So what is dy by dt? Dy by dt is L by y and dl by dt. Dl by dt is, what is dl by dt? Dl by dt, we know that it is u, so this is u. And what is L by y? As you see, this is a triangle and this is theta. L by y is simply cosec theta, means sec theta. So this is sec theta. So u by cos theta, because sec theta is 1 by cos theta. So this is the fourth one is the correct. Now we move to our next example. A block of metal weighing 2 kg is resting on a frictionless plane. It is stuck by a jet releasing water at a rate of 1 kg per second and a speed of 5 meter per second. Calculate the initial acceleration of the block. Now, again, we use some differential uh, equation here. From the Newton's second law of motion, we know the F is m into A. Okay, F is m into A. So, again, we can write down A is d dt of V. Okay, but here am is also variable, so this is not the situation here. So we can modify this equation with the help of this, like f is d dt of p. What is p? P is the momentum, so we can write down p like p is mv. Okay, so take m and v are both are variable, so we can use the chain rule, means first we take m as a fixed, so m dv by dt, and then plus v of dm by dt. From our example, we can see that P is fixed here. So dv by dt is 0. So we can write down simply F equal to V dm by dt. Okay. So using the differential calculus, we modify our second law of Newton motion according to our problem. Okay. So what is V here? V is 5 meter per second, and dm by dt is given as 1 kg meter per second. So this is 5 Newton. So force generated here is 5 Newton only. So here you need to find out the acceleration. So acceleration is simply A is F by M. So what is F? F is 5 Newton and 2 kg is the mass. So this is 2.5 meter per second square. So using differential equation, you can actually uh, modify the equation according to your problem. Okay. Now we take our third example here. The two balls A and B are masses 100 gram and 250 gram. Respectively, are connected by a stretch spring of negligible mass and placed on a smooth table. When the balls are released simultaneously, initial acceleration of the B is 10 centimeter per second square westward. And the direction is given for ball B. Now, what is the magnitude of the direction of the initial acceleration of the ball? So the situation is here is simple, like two balls are connected through a spring, say like this. This is ball A, this is ball B. Now, initially they are in rest condition, means there is no momentum for the system. So we can take the initial momentum, that is Pi is 0. Okay. So this is the conservation of linear momentum. We know that the conservation of linear momentum, initial momentum is 0. So P of B of F means final momentum of B and final momentum of A is also 0 because initial momentum are 0. So what is momentum? Momentum is rate of change of momentum. We can take the derivative of this equation with respect to time t. So simply this is equal to del P B of A by delta t, and this is del P A of F by delta t is equal to 0. So if delta t tends to 0, you can replace delta by d. Means if delta t tends to 0, very small, then we can write down ddt of P final and ddt of P of A F is equal to 0. Now, uh, P of BF is MB and the velocity of B. So simply you can write down the MB and ddt of VB, and here it is M of A and ddt of V of A is equal to 0. Okay. So as you see, the acceleration of the B is 10 meter per second square here. ঠিক আছে? So we can write down like this MB. What is MB? MB is 250 and this is equal to 10 plus MA is 100, and we want to find out the acceleration. So this is A. A of A, capital A. So A of capital A will be minus of 2500 divided by 100. So this is equal to minus 25 centimeter per second square. Minus sign signifies here if the body B move westward, it A will move eastward. Okay. So using a differential technique, you can easily find out the solution of any numerical problem. So I conclude here. In the next lecture, I will discuss about uh, the use of integral calculus in solving the numerical problem in physics. Thank you. Please like, subscribe my channel, and also press the bell icon. Thank you.